So far, we know about the finite deformation theory, right? And from the last lecture, I just start teaching about the small deformation theory. So you remember the main assumption. The magnitude of gradient of displacement is very, very small. That's a main assumption for small deformation theory. And based on, we calculated the volume change in small deformation theory. And today, let me talk about the change of surface. In finite deformation theory, change of surface, so that equation will just look like this. F minus T and dA. Here, N is a normal direction. So when there is a surface, N is the vector normal to the surface. dA is a area, very small area. And F, deformation tensor, J, determinant of deformation tensor. Here the lowercase n and dA is a surface direction and magnitude of that surface at current configuration. You remember? And okay, so our deformation gradient can be written by displacement I is identity matrix. Then this is current material vector equal deformation gradient U plus I and initial material vector. Because this is a F. And let's look at that equation again. dx equal U dx plus dx, right? Then current initial material vector equal minus U dx. And here I like to use the assumption for small deformation. So that assumption is that current and initial material vector are very similar because the displacement is very small. Then we can have an equation I minus U and dx. So watch this. Watch this. This is an inverse. Inverse of deformation gradient, minus 1. Here F, gradient, deformation gradient give a relation between the initial material vector and current material vector. So we can calculate the current material vector from the initial material vector by using deformation gradient F. But how about here? We can calculate the initial material vector from the current. So using the inverse of deformation gradient. So finally, in small deformation theory, N dA equal determinant of Jacobian become 1 plus divergence U. Okay? Determinant of Jacobian was a volume change. I minus X U transpose and dA. So volume change, and this is a inverse of transpose of matrix F. So equation changes quite a little bit. Now let's see what happened in Green-Lagrange strain tensor when we use the small deformation theory. So when we use the assumption for small deformation theory. Green-Lagrange strain tensor. So it was defined by 1/2 X U transpose U plus this was a Green-Lagrange strain tensor. So if we use the assumption for small deformation, then this part, we can neglect this part. So it becomes 0. So this term is very small. And then 1/2 X U transpose, we have only two terms, U, like this. We have only two terms. Right? And here we can use assumption for small deformation. U. Then we can write down this equation for current configuration. Transpose plus U. So this is a very well known small strain. So small strain E is defined by that equation. 1/2 transpose plus, okay? This is small strain measure. You know this one, right? Okay, so we are saying this is a small strain tensor. Or linearized strain tensor. Because we linearize the Green-Rognit strain. This is a linear term, and this is non-linear term. So in solid and structural mechanics, our principal unknown, which we wanted to find, is a displacement U, right? So here strain, here displacement. This is the scale of the displacement. So yeah, for example, let's say we have a function y equal. So ax plus bx squared plus cx cubic, something like that. This is a first order term. You can have here a0 also. Constant term, right? This is constant term, and what's this? This is a linear term. This is a cubic term. Square term. Cubic term. So we are saying this is a linear, and this is non-linear. Right? So if there is some system, usually in physics, all the system is a non-linear system, but non-linear system is very hard to solve. So to solve that kind of very complicated non-linear system, first of all, we need to linearize it. If we linearize it, then we can solve. So we linearize, once we linearize Green-Rognit strain, or once we apply the assumption for small deformation, we can get small strain tensor. Okay? So the small strain tensor in tensor form Ij equal 1/2 Ui, Uj, let's say Uj, xi plus partial Ui xj. Okay, so I like your time. Can you write down all the component? Actually, this is symmetric, so you need to write down only. Okay, so only 6 components. Okay. What's this component? Strain 1, 1. Put the 1 u1 here, x1 here, u1 here, x1 here. Same, right? This term and this term become same, right? So this becomes just u1, x1, right? And how about next term? Next term just become, put I equal 1, j equal 2. So 1 over 2, x equal 1. x1, u2 plus u1, x2. Here u2, x2, u3, x3. Similarly, you can write down all the term, right? So, in undergraduate school, maybe you use the x instead of x1 and y instead of x2. You remember? This is a very well-known small strain tensor, small strain measure. Okay. Now let me look at the length change. What happened in length change when he used the small deformation theory? So in finite deformation theory, the lambda is an increment of length of very small vector, right? Equation was like this, and transpose Green-Lagrange strain tensor n plus 1 minus 1. You remember this equation? N was initial direction. I mean the unit vector at initial configuration. So we derived this equation maybe in last week. Okay, then let's see what happened in this equation. First of all, because the Green-Lagrange strain tensor is linearized to the small strain tensor, let's put the small strain instead of Green-Lagrange strain. Then lambda equal same equation n transpose small strain n plus 1 minus 1. Then let's move minus 1 to the left hand side. Then lambda plus 1 equal 2n transpose n plus 1. Okay? Then let's square both sides. lambda plus 1 square equal 2n transpose n plus 1. Right? Then here lambda square plus 2 lambda plus 1 equal 2n transpose n plus 1. So in left hand side and right hand side, we can remove the 1. And lambda is a change of ranks, right? So lambda is a very small value in small deformation theory. So scale of lambda is much smaller than this. So we can get rid of this. So finally, in small deformation theory, lambda become just n transpose n. This is equation we have. So equation become much simpler, right? So let's look at this equation. How about the lambda E1? Let's put the direction vector, base vector of coordinate system in x direction or one direction. Then it gives us E1 transpose small strain tensor E1 give us just E11. So similarly, lambda E2, E22, lambda E3, E33. So in small strain tensor 3 by 3, E11, E22, E33, E11, E22, E33. This is a diagonal component of small strain tensor. It mean directly the ranks change in 1, 2, 3 direction. Right? This is, we already know about this, right? But in undergraduate school, you don't know why we have this kind of definition. So I think the professors are teaching more physically. But you are now in graduate school, so you need to understand everything very exactly, right? This will help you. And now let's you look at the angle change. In finite deformation theory, sine theta n x n y equal 2nx transpose Green-Long strain tensor and y. 1 plus lambda x, 1 plus lambda y. Here, because deformation is small sine theta is similar to just theta. Angle is also small, right? And then Green-Lagrange strain tensor is similar to the small strain tensor. And then here let's look at this equation. Lambda is a length change. Is a much smaller than 1. Lambda x. Also lambda y is much smaller than 1, 2, right? So 1 plus lambda x, 1 plus lambda y is 1, just 1. Yeah, for example, 1 plus 0.0001 multiply 1 plus 0.0001 is similar to 1, right? So let's apply this condition. Then left hand side theta, okay, n x and y equal just 2 nx transpose small strain and y. So in other words, so let's divide by 2, 1 over 2 theta nx and y equal nx e and y, right? Okay, here let's put the E1, E2, 1 over 2 theta E1, E2. E1, E2 are base vector in x and y direction. What happened? E1 transpose E2. This gives us strain 1, 2, right? Off diagonal component. Strain 1, 2. Similarly, we can calculate strain 1, 3, strain 2, 3. Right? Watch this. What's the meaning of this off diagonal component? Meaning of the off diagonal component is half of the angle change, right? Not the full angle change, half. Here. Half of the angle change, right? Half of the angle change. So off diagonal is half of angle change, diagonal length change. Okay. E11 is a half of angle change between two vectors, E1 and E2. Strain 1,3 is a half of angle change between E1 and E3. And this is a half of angle change between E2, E3, right? So this is a small strain tensor. It's a measure to the for the relative displacement when deformation is small. So diagonal term physically mean length change in the base vector direction, and off diagonal term physically mean angle change between base vector. Okay? Okay, so let's say we have a body here, and I cut this body with some normal vector n. I cut this body. And tangential vector is t. Then we can calculate the lambda n. This is your length change in n direction, normal direction, equal n transpose and strain n. Right? So n is a normal direction to the surface, right? So we are saying this is strain and n. This is a normal strain. Normal strain, because this is calculated from the normal vector normal to the surface. And 1 of 2 theta n t equal n transpose t, strain and t. This is shear strain. So even the n and t vector is not a base vector, we can calculate the shear strain and normal strain, length change and angle change for any arbitrary vector. And especially I like to introduce the one more strain, engineering shear strain. Engineering shear strain equal 2 strain and t. We multiply 2. So it becomes just angle change. In undergraduate school, we are frequently using engineering shear strain instead of a shear strain. So we can write down engineering strain gamma and t. Engineering shear strain and just shear strain are little bit different. So engineering shear strain is twice of shear strain. And engineering strain directly mean full angle change. But shear strain mean half of angle change. So engineering shear strain have a more physical meaning, right? So people like to use engineering shear strain. Okay? Okay, let's give you some example. You remember the problem we considered before? It was this was the original body and stretched, something like that. Right? You remember? What was the gradient? Deformation gradient. 1 plus alpha, 1 minus beta, 1, 0, 0, 0. 0. Is that correct? Okay, and 0, 0, 0. Is that correct? Then we can calculate the Green-Lagrange strain. 1 over 2. F transpose F minus I. 정호, can you write down this here? Very simple calculation. If you want, you can do anything. So this is just diagonal matrix. So this calculation is very simple, right? Because this is diagonal. So if we multiply, transpose of diagonal is also same matrix, right? So multiplication of two diagonal have just a square in each diagonal term. Yeah, if you want, you can, write down the full matrix and then calculate it. So you need to, result should be a matrix, right? That's just a scalar, right? Okay, right? Then, can you solve the inside of this two term? So equal, and apply 1 over 2 to. Okay, then. Okay, yeah, this is correct. This is Green-Lagrange strain tensor. Okay, then how about the small strain tensor? From this, we can calculate small strain. Alpha and beta is small. Then what happened? So you need to write down small strain. Alpha and beta is very small. You cannot sum. Then beta, right? This is small strain tensor. Nice job. Okay. This is a finite strain, Green-Lagrange strain measure. So here we have a square term, right? But deformation is very small. We can have just this result, alpha minus beta, right? You know the definition of a strain. So originally we have a length L, okay? And length increased. That amount of increase is the 1 plus alpha L. So we can calculate strain 1, 1, right? So original length, okay? And final length, 1 plus alpha L minus original length. What's this? This is just alpha. You know this definition, right? So definition of normal strain was L delta L. In undergraduate school, you run like this, right? And it gives us alpha, same thing. But this is not true for finite deformation theory. So this definition is only okay for small deformation theory. Okay? So anyway, so similarly you can calculate the minus beta, right? Okay. And then we also, how about the strain 1, 1? Strain 1, 1 is alpha, beta, minus beta is strain 2, 2. Normal strain. This is all the normal strain. During that deformation, is there angle change? Angle change between E1 and E2. Or there are some E1 and E2 vector here. It's 0. How about the E2 and E3? 0, 0. But if the n vector equal 1 over square root 2, E1 plus E2, and t vector equal E1 minus E2. Is this normal? This is normal vector, right? Normal to each other. Let's use this n and t and then calculate the angle change. Okay, can you do that? So we can simply that angle change 1 over 2 theta and t equal square root 2, 1, E1, E2. So 1, 1, 0. Oh, sorry. Transpose 1, 1, 0. And then matrix alpha minus beta 0. Square root 1, 1 minus 1, 0. What's the result of this? Is this 0 or not? Can you calculate this? So, how can I? What's the answer? You need to have some number here. That's a half of angle change. So it means that angle change means the angle change between two vector at initial configuration. N is this direction, N, and T is this direction, T. Oh, sorry, T is not this direction. Y is minus, T is this direction, T. This surface. What's the number, 정호? Can you calculate that? Simple matrix calculation? Not yet. Okay. Okay, so 1/2 and 1, 1, 0, and here alpha, beta, 0, right? Equal 1/2 alpha plus beta. Yeah, there is angle change, right? So the change of angle and length change depends on how you choose the vector, right? Direction vector, right? Okay?